you every single grade, and that's the story of the evolution of Wade.
Oh man, I'm tired of getting run over by that train in the intro. Whew, man. Anyway, AB, it's time for 7-4. Let's do some more rotations and volumes and really cool stuff. All right, letter A. Quickly graph all this information. You should not spend very much time doing that. You should all be graphing masters by now. X equals 0, y-axis. X equals y squared, sideways parabola. Not y equals x squared that we're normally used to, but x equals y squared. So you get this twisted sideways parabola. Technically it doesn't go like this. It actually goes like this and inverts as it twists. All shapes do that when you do an inverse, okay? So technically that's what happens. All right, so then what else do we have? Y equals 2. Go up to 2 on the y-axis and put a horizontal line. All right. And then y equals -2. Go down to -2 on the y-axis, horizontal line. Notice I didn't put 2 like up there. Play the game. Go low enough where you can enclose a little shape here so you don't go way up here and there's nothing enclosed. Eventually, yes, the sideways parabola would catch up to 2, so we kind of put it low and you kind of make it enclosed, you know. Okay, so you have to be artistic here. Now let's go back to that y-axis. Let's go ahead and put it in now and kind of darken that in. So do you see the one shape in the world that is contained by the sideways parabola, 2, -2 in the y-axis? It's here, it's there, it's here, and it's there. There's your little shape right there. Okay, now, there's the graph. Check it off. B, set up the volume of this region, capital R, rotated or revolved around the y-axis. So today we're going to revolve this way, whereas in the past we've revolved around a horizontal axis. We're going around a vertical axis today. So imagine this shape. Let's go ahead and draw a dashed line here. Not to be confused with an asymptote. It's not an asymptote, but it looks like it. It's the y-axis. It's the axis of revolution. Okay? So we're going to take this shape, we're going to spin it around, and look what happens. Here's its ghost image over here. Okay? That's its mirror image across the axis of rotation. The top corner goes off the board, goes around, goes in orbit around the y-axis, and just makes a giant circle. The bottom corner also comes off the board, rotates around into a giant circle, and the circles get smaller and smaller and smaller, and they pinch all the way down to nothing, and then they grow again, and then they're larger and larger, and you get kind of an hourglass when you put it all together. It's very cool. Okay, find that volume. Well, one very important thing to notice is that the radius of each circle, from the edge of the circle to the center of the circle, or, as we say in calculus, from the outer form that's carving the shape to the axis of rotation, that radius right there is a horizontal distance, not a vertical distance. So basically we're going to have y's, not x's. All right, so I already want you to be thinking about that mentality. The fact that we're stacking in a y direction and not an x direction, that's a big difference here. And that's where students can mess it up right there, okay? So let's see if we can set up this volume. All right, the volume of this solid is, remember it's pi r squared, it's just a bunch of infinite pi r squared circles, and then the pi comes out to the front. The integration can handle adding infinite things, adding infinite circles together for you, all right? And then pi infinite r squared. Now remember our formula, the way that we write it. Outer minus axis squared. That's basically horizontal distance is what it is. It's the radius. And you can do horizontal distance or you can do our little outer minus axis trick, okay? Now, first, before we establish this, remember there's also a minus inner minus axis squared for any kind of hollow part, okay? But there's no hollow part. This is a solid shape. The entire region, capital R, that we initially mentioned goes right up against the axis of revolution. There's no gap, so there's no hollow part. So you will not have to worry about this part, not this time, okay? Now the stacking, this is very important to stack it correctly. We are not stacking from here to there. We're stacking the circles from there to there. That's why it's good to draw the picture. It doesn't have to be fancy, and I'm not much of an artist, but even just drawing one circle for yourself and looking at that will help you. So we're going to stack from -2 to +2. Put that here. And then remember my advice from previous lessons. Once you establish the limits of integration, you will then go over here, and since there's no hollow part, this is gone. You will choose your d whatever. You have to choose dx or dy, and I would do that before I do anything else. Okay? -2 to 2, that's stacking in a y direction. So you must use dy today. And that's what we said, go to y world, not x world. Okay? dy, stack, and then we do our formula. You can either do horizontal distance, or you can do outer minus axis, it's the same thing. All right. Outer, who's carving the outside of the hourglass? That is x equals y squared. Let me put that next to outer, actually. X equals y squared, okay? But you have to determine, do you want x by itself, which is called in terms of y? Or do we want y to be solved by itself, which is called in terms of x? Guess what? dy tells you you must have y's in here. So x equals y squared is perfect. Y squared is what we put here. Also, if you did a horizontal distance, if you want to do it that way, isn't it right x minus left x? So you do want x by itself, okay? Now, true, if you take the square root of both sides, it is true that technically it's plus or minus. Y equals plus or minus square root of x. Yes. You would not want to put plus or minus square root of x here because it doesn't match dy. So that's how to make your choice. And if you ever see yourself mixing up x's and y's, that'll be a warning to you to straighten it out, okay? And then all we have to do is subtract the axis of rotation or revolution, and that is 0 because it's the y-axis. All right, so let's go ahead and just clean this up a little bit. So the volume of this hourglass is -2 to 2. It's drop the 0, y squared squared, power to a power, you multiply the power. Middle school math. Okay? And you get y to the 4th dy. Now, you're fine to leave it like that. I have a suggestion though, because we're about to actually go integrate this and find the volume. Going from -2 to 2 is fine, but this shape just happens to be symmetric, and often they are not. But we got lucky this time. We got one that's symmetric. The bottom half is the same volume as the top half. So if I were you, I would integrate from 0 up to 2, just there, and then double it, and you'll get the same answer, but more efficient, okay? So this is a fine answer, or double the whole thing, so put a 2 out in front, 2 pi, 0 to 2, stacking this way, and then same y to the 4th dy. Better, faster, okay? I mean, you are really doing calculus now, let me tell you what. We are in the heart of calculus. We know derivatives backwards and forwards, we know integration backwards and forwards, and now we're applying it to real life problems. So this is your better answer, because when you integrate, I would rather plug in 0 than plug in -2. You can make mistakes, okay? All right, that's the answer to B. Now, other board, letter C, find the volume. Well, we just did the integration, now we just have to integrate it. So let's just take this thing that we had over there. I guess we don't really need the equals. I don't know why I put that there. Anyway, let's just take this and let's jump into it. 2 pi, integration of y to the 4th, y to the 5th over 5 from, evaluated from 0 to 2. All right, plug in the top number first. 2 to the 5th. You need to know your powers of 2 in this class. 2 to the 5th is 32. That was one of our highest ranked, most important things in Integrated 3. At the end of the year, I gave you a list of top 20 most important things. Powers of 2, that was one of them. So you get 2 pi, 32 fifths, minus, plug in 0. 2 pi times 0. drop it. No cross cancellation, that happens sometimes. 2 times 32 is 64 pi over 5, or you can put 64/5 pi on the side, doesn't matter, and that is the exact. Of course, that's an irrational number, so you could never really ever express it on paper because that goes forever with no pattern. Pi does, right? But that irrational number is roughly what the volume is. So in letter D, we need to graph this quickly, and then we need to set up the volume again. All right, here we go. So natural log, okay, remember the secrets of graphing things like natural logs. Plug in a number that makes the inside 0, plug in a number that makes the inside 1, and that's really the quickest, easiest way to graph a lot of things. The other strategy is go get the x and y intercepts. That helps with other graphs very well. Maybe not natural log. So in this case, let's plug in something that makes the inside 0. How about x equals -1? Y equals the natural log of 0. That's what we wanted, a 0 on the inside. Natural log of 0, impossible. You can only do the natural log of a positive number. Does not exist. Oh, -1 is the vertical asymptote. No wonder it doesn't exist. It's one of our 3 types of DNEs in math. All right. Now the other strategy, plug in the number that makes the inside 1. How about x equals 0? X equals 0. Y equals the natural log of 0 plus 1 is 1. But the natural log of 1, ironically, goes right back to 0. Aha, so it hits the origin. Interesting. Most natural logs do not. Okay, so there's that. And now know your natural log curve. It tears away from the vertical asymptote slowly, goes up through there. Easy, right? Y equals 2. Y equals 2 is a horizontal line at 2 on the y-axis. Now play the game. Don't put it up here because it's not going to enclose the space for a very long time, right? Just like put it down here. Let's just call that 2 right there. See, I'm trying to enclose a little space in there, right? It's going to be right in here. X equals 0. Y-axis. Same thing as the y-axis. Perfect. Look at that. Little region that they call capital R in the AP test, always. Okay, so there's my space, some kind of little curvy triangle. And from that, we're going to set up an integral that calculates the precise volume of that shape revolved around the y-axis. So the theme today, of course, is vertical axes of revolution, right? So if you take this and you spin it around this, oh, this is going to be weird because we're going to have a vertical asymptote here, and then this is the other dashed line in math, an axis of revolution right here. And they mean completely different things. This means it does not exist, and this just means spin it around. So maybe we'll draw this over here just real quickly. We'll draw this, and we're going to spin it around the y-axis. So here's its ghost image over here, all right? It's a ghost image. Hey, usually we do this lesson right around Halloween. So that's perfect that we have a ghost image. I guess I should be doing something today like, you know, sitting here talking to you with my head sitting in my hand at the same time. Oh my gosh. Anyway, enough of the jokes. So this space, when it goes around the y-axis, the top corner goes around, makes a big circle. Oops, I didn't quite connect that there. And then you get smaller circles and smaller circles. And when this thing spins around, it kind of makes like a top, sort of, or like a funnel, but it's solid, so you can't get any liquid into the funnel, you know, or any oil in there. So anyway, find the volume of that shape. We'll at least set it up. Okay, volume equals. Now, do you notice that the radius of each circle is a horizontal distance, if you want to do it that way? Right x minus left x. So that means we're going to have all y's again when we do this, okay? So the volume is just a stack of pi r squareds. And not just pi r squared, but an infinite stack of pi r squareds. That's where the integral comes in. So pi infinite r squareds. Okay. Outer minus axis. Oops, goes there. So outer minus axis. Okay. Who's carving the outside of this shape? That would be this little curve right here. That is your natural log of x plus 1. That's what's carving the outside of the shape. All right. So the outer, now some of you know that this is not perfectly correct. I'm going to go ahead and put it down anyway, and I'm going to show you how to tweak it. So let's just go with the flow for right now. The outer is the natural log curve. Great. Minus the axis of revolution, which is the y-axis, which is 0. Now, where are we stacking? Where are we stacking the circles here? We're stacking the circles from bottom to top, right? Because we're stacking this way. 0 to 2. I just covered that up, but that was a 2 right there. 0 to 2. Stacking. Wait a minute. 0 to 2, that's a dy direction, not a dx direction. See, this is an x-axis type of direction, right? Y-axis or dy. So 0 to 2 matches dy, and I've seen students do this before. And right before you walk away, you need to go back and say, hold on a second. If the circles are being stacked in a dy manner, I shouldn't have x's in there. This is an all y's problem. What are you doing in there? So when I put it down, I was just playing a game, but some of you noticed right away that was wrong. We need to fix that. Yes, the natural log is what is carving the outside of the shape. Absolutely true, right? It's making that happen right there, but it's not in terms of y, and we need it in terms of y, which means solve for x. In terms of y means get x by itself, okay? All y's. So we need to alter this, and you can do this first or you can do it now. It doesn't matter when you do it, just do it at some point. So the alternate form of the same equation, y equals natural log of x plus 1. Let's go off here to the side. Y equals natural log of x plus 1. How do you get x by itself? First, get rid of natural log. How do you get rid of natural log? E to the power of will destroy natural log. And if you do it to the right, you do it to the left. E to the y equals x plus 1. Subtract 1 from both sides. And x is by itself, which is equivalent to e to the y minus 1. So natural log of x plus 1 is identical to x equals e to the y minus 1, written differently, but the same equation. And you see, instead of using the x version, I can use the y version, and that's correct. E to the y minus 1. Okay, let's write that a little bit neater for our final answer. Pi 0 to 2, infinite r squareds, e to the y minus 1 is the little horizontal distance in there. Quantity squared dy. We're not going to find the volume of this today. To find the volume, by the way, you could not add 1 to the power and divide by the new power, because then when you divide by the chain rule of e to the y is also a variable, e to the y. You can't do that. You would have to FOIL this out with itself and then just do basic exponential integration to get there. So be careful. That would make a good bonus, by the way. A really good bonus, actually. Thoughts. Thought bubble. What kind of bonus could I put on the next test? But anyway, yeah, that's perfect. That's fine right there. We're not going to find the volume. Okay? That'll do it. That's it. So now go try some homework and see if you can master vertical revolutions.
Hold it now.
AB 7777-4. You stupid idiot. All right. The other place you could plug in is plug in the thing that makes the inside what? You stupid idiot.
We looked around the city, we finally scored, and now I'm back teaching from a dry erase board. Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
Wow.